All right, welcome to our fifth video of Unit 4. This one's talking about calorimetry and enthalpy. So calorimetry is the measurement of the heat flow into or out of a system for chemical and physical processes. It was invented by this man named Antoine Lavoisier, Mr. L. Sorry, can't speak French too well. Now, he basically did quite a bit different calorimeter than we tend to use today. He actually involved measuring how much ice was melted when you have a reaction. But he kind of started it all. And calorimetry is how we get, especially this number right here, which stands for calories. You can track how much energy comes from some reaction or, in this label, food. So this is a calorimeter. This is the calorimeter that we'll typically be using. It's called a coffee cup calorimeter. I'll let you guess what the main ingredient of it is. Oh, that's right, coffee cups. Basically, you take a coffee cup, put it inside of another coffee cup, typically styrofoam. The main reason behind that is styrofoam doesn't really transfer much heat through it. It's kind of a sketchy little compound when you actually look into it, so don't. But you put a stopper on it, and then you put a thermometer and basically a stirring rod in it. So you kind of seal the reaction in the coffee cups, track how much heat is coming, and stir it around to make sure things actually happen. A more precise calorimeter is called a bomb calorimeter. Now, no, it's not because you're building a bomb with it, though you are technically building a bomb inside it. Basically, you got a container, you fill that with water. Inside that container, you put a small container. Typically, those are have two ignition wires in it instead of, like, basically you put the reaction in here without reacting and then ignite it once it's sealed up. That then generates heat, which generates into the water. You have the water to stir it around so that the heated water disperses, and then you track the temperature that happens. We actually know exactly how much heat you need to raise 1 degree of, the heat required to raise the temperature of water by 1 Kelvin. So it was actually very accurate, but this will work most of the time. So the heat flow of a system at constant pressure is what we call its enthalpy. And that is denoted by H. I don't know why H. If you think about it, why not E? Well, typically energy is denoted by E. So enthalpy, I guess, is the next best thing they could actually get. Anyways, it's typically measured in joules. That's a lie. It's also sometimes measured in kilojoules or calories or kilocalories, but most commonly joules. This is also just, we consider it the total energy that a sample has. So it's basically all the energy that you got from your sleep, plus the energy that you got from running a couple warm-up laps, plus the energy that you got from the food that you ate, minus the energy that you spent running around type thing. That's just the total energy that you've got in whatever sample. Calorimetry basically is interested in the amount of energy that is the energy change from a reaction, typically energy generated or absorbed. Now, to solve for the energy absorbed or released, welcome to your basically favorite equation. Now, that was a complete lie. It's probably going to be one of your least favorite equations. However, you're going to know this really well. My hope, at least. Hopefully. So, we're going to explain these letters in just a bit. To calculate the energy absorbed and released using Cm, follow that equation. Now, I lied in the previous slide. I thought I had a slide describing the terms in it, but apparently I'm not. So, they're both the same equation, except on the previous equation, we had M here instead of an N. M stands for mass, which is typically grams. N stands for number of moles. So you basically have either grams or moles. On the previous one, we had CS. That stands for specific heat capacity, which we'll describe in a bit. Cm stands for molar heat capacity. The specific one deals with grams, the molar deals with moles. It's really all you got to remember. And Q represents the amount of heat that is absorbed or released from the reaction. I have no idea how they got heat from Q. Like, that's even worse than enthalpy. But whatever, we'll just kind of deal with it. All right, so the equation you use is dependent on whatever heat capacity you are given. So if you're given the specific heat capacity, use the specific heat capacity equation. If you're given molar heat capacity, use the molar heat capacity equation. It's quite doable. Si se puede. So, example time. How many joules of heat are absorbed into 25.0 grams of water if its heat is raised from 25.0 degrees Celsius to 26.4 degrees Celsius? Well, typically you're given a heat capacity. Unfortunately, in this question, we don't have that. So everyone get up and let's run around screaming and panicking. Okay, please don't do that. Like, it would just be a bad idea because we actually know the heat capacity. We had an entire unit on heat capacity. By unit, I mean video of heat capacities. Hopefully you remember that the specific heat capacity of water is 4.184 joules per grams Kelvin. I may have actually taught you Celsius. It's the same thing. I recommend starting to think in Kelvin, and if I taught you that earlier, that's awkward because I can only blame myself, but deal with Kelvin for now. So, back to that equation we had. We had Q equals, in this case, we're given specific heat, so we're going to use M times CS times delta T. All right, so M, in this case, is going to be our 25.0 grams. Remember, M stands for mass. Grams are a type of mass, well, a measurement of mass, so that's our M. Our delta T represents our change in temperature. Now, we've mentioned this before, but we're trying to see how much temperature we rose or dropped when we went from 25 to 26.4 degrees Celsius. That's pretty doable. Take 26.4 minus 25.0. You should get 1.4 degrees Celsius. Notice that is a positive number. That means that in this reaction, we are rising our temperature by 1.4 degrees Celsius. And we know our specific heat capacity, so we're set. We're solving for Q in this case because they're asking for joules of heat. Again, heat represents, or is represented by Q. So our Q equals our grams, which are 25.0. Our specific heat capacity, which is 4.184 joules per grams Kelvin. Now, before you ask me if we have to write the units, I'm just going to say yes. Just write the units, get over it. Times 1.4. This is actually in Kelvin. We took our temperature in Celsius. They're actually the same difference. So a rise of 2 degrees Celsius is going to have the same rise as 2, like, it's going to be the same as saying you have a rise of 2 Kelvin. It's the same. So you can change them all you want. If you want proof, convert these both to Kelvin and then subtract them. You'll get the same answer. Anyways, 25, 4.84 times 1.84 gets you 146.44 joules. And that is our final answer. So again, the issue I'm expecting you have is how do we get the Kelvin? A change in Celsius is the same as change as in Kelvin. So if you rise 2 degrees Celsius, you can also say you've risen 2 Kelvin. It's the exact same. Just get used to converting things to Kelvin firsthand. That'll help you pretty well. But that's it. You find your mass, find your heat capacity, delta T, plug them in. Sometimes they're going to give you your Q, but then you just figure out what you're missing and just solve from there. All right. So I'm going to say pause the question in just a bit, though. Sorry, not yet. Let me read the question, then I'll let you work. So determine the energy as heat needed to increase the temperature of 10 moles of mercury by 7.5 Kelvin. The molar heat capacity of mercury is 27.8 joules per Kelvin mole. Now go ahead, pause the video. Good luck. Come back in a bit after you've tried. All right. Hopefully you've tried. So let's work this out. Determine the energy as heat. Hopefully you remember that represents Q. Needed to increase the temperature of 10.0 moles. Now we're dealing with moles. Unlike last time, that's going to represent it in. We're using our second equation, not the one with grams. But we're raising the temperature by 7.5 K. That is our delta T. The molar heat capacity is 27.8 joules per Kelvin mole. That is our Cm. Again, molar heat capacity. Mr. Booth, how'd you know it was molar heat capacity? Well, A, it says, molar heat capacity. B, moles. Just helping you out there. All right, so Q equals, this equation, just remind you, N Cm delta T. So we have 10.0 times 27.8 times 7.5, and that equals 2,085 joules. So there you go. It would take 2,085 joules to raise 10 moles of mercury by 7.5 Kelvin. That's basically what we solved for. All right, here's your practice. You can read the problems. I'm not going to read them for you. But as always, thank you for watching. Enjoy the practice and have fun.